And, yeah, so one of you want me to help?
Clip as such, or here, I'll let you do it.
Yeah, sure. I think with the
Let me
t-shirt.
not pretend I know what I'm doing.
Yeah, I think with the t-shirt, we're just going to improvise here. So right about there is usually pretty good, and then that you just put in your pocket.
Perfect. Is there a button which button do I?
This is, and it's on, so you're good.
All right.
And if you want to click forward, you can use that if you want, if you prefer. Okay, great.
Hey, I'm Scott Sinno with the NASA NCCS here with Ellen Salmon today, who unfortunately had to vacate a little bit early. I wanted to tell you about the large-scale Linux software RAID system that we've put together that's now part of a proper zoned virtualized environment. And this is more traditional hardware virtualization rather than containers, which we've been discussing for the last couple presentations, although I am quite fond of container technologies. I'll go ahead and move past this slide since Ellen already described what our group does in a much more articulate fashion than I'm going to. So some of the challenges we had, security challenged me with some criteria that's not typical of a zoned ecosystem necessarily, and that no hypervisor can have direct network connectivity to any of the VMs. We need to segregate VMs into separate zones by risk class and maybe the nature of the science or the principal investigator behind the project. No writable shared storage between any of the VMs within the environment, and the hypervisors, of course, have to exist in their own zone as well. This started as a proof of concept system, so a lot of the hardware I needed to use were hand-me-downs from the larger, more conventional cluster that runs most of the NCCS jobs still to date. We used exclusively JBODs and commodity, not SATA, SES, SAS, commodity SAS disks, and nearly exclusive leveraging of open source software. We tried to initially start with Gluster, which was promising for some time, but unfortunately as we scaled the environment, that no longer seemed to fit our needs. So we went with a software stack that, as you can see, pretty dang open source. We're still with CentOS 6 for our hypervisor layer. We're using KVM, QEMU, very classic true virtualization software suite that many of you may be familiar with. Puppet and Puppet database, and that database turned out to be quite key for managing some aspects of the environment. We are using custom built LTS kernels straight from kernel.org. I've never been terribly thrilled with Red Hat's schedule of kernel evolution per se, and moreover, using an LTS kernel allows me to provide a consistent kernel across not only the hypervisors, but all guests. And for softwares that require building modules against the Linux kernel, I only have one kernel to build against rather than potentially many. We're using Linux MD80M for our software RAID layer. GPFS 4.1 is the primary file system backing, and we are using Mellanox OFED to provide a genuine virtualization layer. All the VMs are fully InfiniBand aware, connected, and have a functional RDMA layer. So this is kind of the core of what enables it. So here we have two what I'll call storage hypervisors. Each with cross-connected JBODs. Now, some of the JBOD drives are just left as bare. Some of the colors must not show up terribly well here, but some of the drives from these JBODs are set aside just as bare drives, and others are assembled into RAID 6s. Now, the RAID 6s are just passed up. The RAID 6s are then defined as LVM devices and passed up directly as block devices to these various NSD serving guests that we have out here. And so, you know, we have a pair of NSD servers for, say, the Above project, another pair for the Colette project, another pair for the HIMAT project. And if one of these is more of a has higher I/O bandwidth needs or higher HA needs, we take some of those bare drives and pass the bare drives up to both sides such that they can be defined on both NSD servers redundantly. Those are so that gives a legitimate dual path to GPFS. So say if we passed all the bare drives on each JBOD to Colette 102 and 101, then those could be defined with both paths and give you a higher availability solution, as well as a higher write I/O throughput than RAID 6 is able to offer. So by splitting the storage in this manner, we're effectively giving these storage slices to a set of VMs or a zone of VMs within the cluster. And this is just a simple, they do have connectivity back to common support services like LDAP mail. We use Ganglia as a cluster monitoring mechanism, but they're not able to communicate with each other in any way, shape, or form. The Puppet database turned out to be essential in it actively updates a database with our entire inventory and captures everything. So we have a very up-to-date inventory of what's where, what guests are on what hypervisors, how many resources have been allocated to any given set of guests. The database also provides an automated way to configure Slurm. If we have a set of nodes with 10 in it and it suddenly expands to 20, well, there's no need to go in and redefine the Slurm configuration. We have separate Slurm partitions per zone as well. So the database will actually rewrite the Slurm configuration itself to encompass whatever nodes are in that set of VMs on any given day. It also provides, if any of you are familiar with the PDIS utility, very common in Unix administration for bulk systems. It also gives us a way, this may be kind of hard to read, but we've written a command called pupsh, which is really just a front end to PDSH, but it enables you to utilize an SQL query as a selection mechanism. So if I want to say, run a command on all Debian systems with more memory than X, I can do that. If I need to shut down all the virtual machines that are part of a certain hypervisor range because we have a power outage coming that day, we can do that very, very straightforwardly and very, very easily. And that's just a snapshot. Unfortunately, I couldn't bring my laptop and demonstrate the entirety of the Ganglia configuration, but that's one example. We use Ganglia as a means of letting users see what systems they have jobs running on and how well they've got their set of nodes loaded. Currently, we're supporting about 15 petabytes of raw disk and a mix of 4 TB, 6 TB, and 8 TB drives. About 12 terabytes of that is usable due to the RAID 6 and, in some cases, replicated drives in the environment. And we are up to well over 300 hypervisors. Currently, as of yesterday, 674 guests. We're providing some static services with this environment as well. We have a dedicated kind of high-risk data service zone that provides things like ArcGIS. The Earth System Grid is supported. We have a variety of FTP, Apache, and Tomcat servers instantiated in the environment as well. And mine's pretty short, so happy to entertain any questions.
All right, thank you, Scott. Questions for Scott? So I'm sorry, this is a really basic question, but I am helping manage the conference. So are you presenting, is it a file system interface? What's the interface again out of these devices?
So the interfaces are primarily shell-driven. Our users come in via shell, and they will execute commands via Slurm typically. Although occasionally there are users who utilize the same pup.sh mechanism to call jobs out there as well. So it's driven that way.
Got it. So they script against when they need to make access or yeah.
Correct.
Okay, got it. Okay, perfect. And then how, is that like then you've built libraries where the applications can talk to that, or is it specifically it's a different kind of workflow? It's not something where it's directly from the applications, they're not directly touching it?
No, all this would be transparent to the applications. There's nothing, we're supporting a full-blown POSIX file system behind that. So that's the interface here. Unfortunately, for better or for worse, within NASA, there's still a lot of legacy codes, programs, and things like that are only going to be usable through a POSIX interface. So we have maintained our focus in providing that kind of thing.
Cool. Yep, question?
Just a clarification. So you're using GPFS, but are you presenting software-based LUNs to GPFS?
Correct. So let's go back to that, the good slide, if I can figure out how. Nah? Can we take me back to slide 4 somehow? There we go.
Slide number 4?
One down, actually 5. I lied. Perfect.
Okay, here we go.
All right. Yeah. So here we have our standard JBot is 60 or 84 drives. So say we have 60 drives in each of these. So maybe on this one we'd take 48 of those drives as for 10+2 arrays. And we pass the array device itself gets passed up as a block device to the virtual machine. The virtual machine is then a GPFS NSD server. On that virtual machine, that block device that's getting passed up to the VM is defined as an NSD.
Okay, so I'm trying to figure out, so does your environment still allow failover?
Yes and no. So that's something we're working towards. In the case where we're passing just bare drives up, then yes, it fails over seamlessly because we've got 2 drive paths defined to the same device. You have a bigger problem with MD80M in that you can't have the same RAIDs assembled on both sides here. So, maybe the node on the right has all the RAIDs that are part of its JBot assembled, and the node on the left has has all its arrays as live assembled over here. Well, you can't have the same ones assembled on both sides. What we're currently doing as a failover mechanism is we have and it's not live yet, so I don't want to oversell it here, but it relies on LVM lockd, and whenever LVM lockd notices that its partner machine is down, it'll unlock that device on the other side, assemble it, and present the LUN up to the VM. And you can do that with KVM QEMU live. You can live attach or live detach a LUN. So that is, we've manually done it a few times successfully, but it's not live in production yet.
Okay, thank you.
Any other questions? I love that. I mean, my guys were working on it when I was at Red Hat. We were working on LVM locking. I thought, who's going to actually use this? So anyway, it's great. Very good.
Small world.
Yeah, that's right. Thanks, Scott.